Well, let's go ahead and get ourselves started. And I'm going to suggest it's very hot in this room, I'm going to suggest we leave these doors open for a little while. If it gets overly noisy out there, then we can go ahead and close them. We've got a smaller group, and with smaller groups I do tend to like to see if we can get a little bit of interactivity. Let's just kind of start out. I'm going to assume the vast majority of folks here are software engineers, software designers. Are there any hardware people here? Okay, we actually have a couple. And how many of you have been involved with a design that has an FPGA in it? Okay, same few people. How many of you actually are in the process of developing products versus, which is, a product that gets shipped to a customer versus, let's say, an operating system or a software distribution? How many are product type people? Okay, and just check the other way around. How many are kind of more software distribution type folks? Okay. And then I guess a couple other checks. How many of you had a chance to see Tomas's keynote? Good. Tomas was awake for his own presentation. And how many of you saw my presentation yesterday? Handful of you. So there's some new folks in here. Some of the material I'm going to cover is an overlap with the material that I presented yesterday. I'll probably try to go through that material a little more quickly. We're going to start out, talk a little bit about some of the challenges there are in terms of implementing neural networks. I'm with Xilinx, so we build these heterogeneous, all programmable devices. So I'd like to talk a little bit about what our device has. We'll then describe what we mean by reduced precision neural networks, and specifically the binary neural network that our research organization developed and we demonstrated yesterday at my presentation. Unfortunately, we're not going to have enough time today for a demonstration, but I will pull up a quick video. And then I'll invite you tomorrow during the demo period, which goes from noon to 2. Stop by our table. We'll have that demonstration running, as well as additional portion of the demonstration, which has a camera, so you can actually put a traffic sign in front of it and see kind of how well it works. And then we'll actually go into that design example and just describe in a little more detail. I can't claim to be an authority on neural networks. What I can talk about is my observations when I see others developing neural networks. And let's try another one. How many have done some research or understand kind of the concepts of a neural network and how they operate? Okay, half the group. How many have not? Have no experience, knowledge, or otherwise about neural networks? Okay, a third of the group. The whole concept of neural network is it really is based on the way the human mind, or at least our perception, understanding the human mind operates. In other words, you get in some pieces of information into a neuron. Each of those pieces of information has a weighting factor, so it generally gets multiplied by this weighting factor. And then all of these weighted inputs then get summed together, and then you look for a threshold. Did we get enough energy, total energy, into this neuron to cause it to fire and propagate its output to the next neuron or collection of neurons? The researchers believe that neural network technology is something that is able to model most scenarios that we are interested in. And so far, the evidence is that these neural networks generally have been working better than traditional techniques in terms of object recognition, voice recognition, signal processing types of functions for recognition than what we have been using. this is an interesting statement. It says it requires less expertise specialization in the target domain. Well, if you were to look at what was done prior to neural networks, there were folks that were doing research. They'd be in audio and voice recognition. There'd be other groups in vision recognition, and then other groups working into other types of recognition. And each field was developing their own techniques and technology for recognition operations. And honestly, there was some overlap, but generally they tended to find these algorithms that were kind of optimized for their particular need. And there wasn't a lot of overlap. So what this comment really refers to is it's basically saying neural networks are able to span multiple domains. As a result, you don't need to have as much expertise into the characteristics of the information that is coming in for your particular domain, which is kind of a good thing. It means that neural networks can be used across multiple domains. You don't need to be an expert in voice recognition, handwriting recognition, vision recognition. The flip side is, I like to say, from my observation of folks developing neural networks, the challenge is it's a bit of a black art right now. In other words, there's folks that have done it. They generally can look at a particular type of problem. They can go and say, based on my experience, having worked with these umpteen neural networks, that a particular architecture is the best architecture. But generally, it's really a matter of experimentation with the depth, the width, the height of these arrays of neurons, how much connectivity you have, and over time you'll develop experience and determine, okay, this particular architecture is the best one for my application. We have reached a point, if you were to again read some of the research, you'll see that early on, the Holy Grail was to be able to do as well as a human being in terms of recognition. And these days, certainly some of the larger networks, if you look at the results, they're claiming that they do as well, if not better, than humans for a lot of recognition problems. So, the challenges, I kind of already talked a little bit about the first case. You have different types of networks. You're looking for different characteristics. You're looking for different capabilities. You may have requirements in terms of speed. In other words, how fast can you do the recognition? If you look at all of us, we are always talking about how many images per second we can process. Certain applications, things like automotive, they're looking at latency. In other words, you want to make sure you recognize the person that's standing in front of your path of your car in time so that you can brake. And right now, if you look at the majority of the engines that are being used for recognition activities, they're all extremely power consumption heavy. There's nothing that's coming close to approximating what the human mind can do in terms of processing recognition per watt. And as I indicated, by the time you get done, you're looking at billions of multiply and accumulate operations. And one of the other challenges is, if you go back to what I mentioned earlier, every single neuron, every input to the neuron requires a weighting factor and a threshold value. You have to apply these in some manner. And if you're doing a typical computer application, and you're running software, that means you're constantly pulling this data in. It's being pulled in from DDR, and so you're talking about moving megabytes of this parameter data as quickly as you can in order to do these multiply and accumulate operations. It can be very taxing on your memory systems and bandwidth in your processor system, and obviously that type of bandwidth also consumes power. And then another challenge is that we are constantly developing and coming up with new algorithms, layouts, architectures for these neural network applications. What was in for 1 year is going to be out the next year, and there will be a whole new technology that has been proposed by someone and demonstrated to be better than the previous generation. So what all this really means is you need a massive amount of flexibility. And as I mentioned, all of this is experimental. Basically, you're constantly taking and saying, okay, I'm going to throw a whole bunch of hardware at this. I'm going to throw a whole bunch of power at this, and I'm going to do a particular computation, and here's my error rate. The only problem is I want to be down here, so then I have to keep re-architecting my network to get to whatever point of recognition accuracy that I'm looking for, i.e. back to my comment about trial and error and lots of effort that has to be put in. I'll quickly go through this slide because I pretty much covered it in my presentation. We also had Tomasa covered in the keynote. With the Zinc UltraScale Plus devices, we have integrated multiple types of processing elements. And so we have, the ARM Cortex-A53s. Many of you are familiar with them. They're standard architecture for running something like SMP Linux, excellent application processors. We have dual ARM Cortex-R5s for real-time applications. How many of you actually do something that requires real-time measurement applications? Only a few of you. And so I'd like to suggest that in the world where products get delivered, and especially when we're talking about neural networks and recognition, we are heavily focused on being able to do things in real time, do it reliably and accurately. And again, my best examples are in automotive and industrial type of applications. You need to be able to recognize something and respond to whatever you see quickly. That can be a safety issue. Speaking of which, those R5s can be run in lockstep. That's the question I asked in my previous session. What's the value of running two processors in lockstep? This is an interactive class, incidentally. Okay, I'm sure somebody knows here. Yes?
In case they get different answers.
Exactly. So, if this is a whole nother topic, I love to talk about. It takes about an hour, but you probably have all heard about radiation. Radiation, can go and strike a memory cell and cause a bit to flip in that memory cell. Most of the time, when we're talking about our PCs at home, our laptops, etc., we don't worry that much about it because the probability of it happening on your particular unit is extremely low. It may take years before you have a single event upset that is likely to disturb something that you are doing. Well, you take something, let's say something's going to happen once in 100 years. Now you go and you deploy 100,000 units in the field, like a car. Now suddenly, that 100-year number means you're going to have 1,000 of these events in your vehicles per year that could be disturbing something. May cause it to miss a critical event, or it may cause a event to occur like, let's say an R5 gets a single event upset. It's running independently, it's responsible for braking function, and it takes a hop, skip, and a jump and suddenly says, apply the brake to the car. You don't want that to happen. So, if you're running them in lockstep, if you get a single event upset, they'll have a difference between the two processors. You'll get an error condition. That error can be pushed out to a different processing element in the system, which I'll talk about. And you can do a safe failure. In other words, you basically say, the R5s are no longer operating properly, I can no longer properly perform, maybe turn a little red light on the dashboard, and then go and reset and restart the system and bring it back up. Speaking of which, we have something called a platform management unit, triple redundant processor. It's used for a variety of different functions. We do include things like all our power management firmware sits on the platform management unit. various error handlers. In fact, that's probably where you want to put all your error handlers that might come in from another system, so that you can have your most robust portion of the system handling system level errors. And if you're doing functional safety applications, you might want to have your most critical code put there. And I have to ask the question again, so what's the value of a triple redundant processor? If you can guess the value of double redundant, you probably can figure out the value of a triple redundant. Yes?
They can make a majority vote.
You got it. Okay, so if you have 3 processors, one of them takes a hop, skip, and a jump due to a single bit upset, its output will be different than the other 2 processors. The other 2 processors will outvote that 3rd processor, and you can continue operation for a while. Now, 3rd processor, a couple possibilities. If the error was simply in the output function of it, it might continue operation. After that, you will resume with all 3 processors providing the same output. Life is good. However, it also could do something like impact the instruction the processor is executing, possibly a jump instruction, in which case it jumps off in the wrong direction, and it will continue in proper operation. So eventually, in that scenario, you do have to do something to get all 3 processors back in sync. So generally, at some point, you will reach a safe point in time, and you will reset or resync all 3 processors. Okay, and let's see, our devices have the Mali 400 graphics processing unit, especially for small embedded applications. Great little processor or graphics unit for displaying 2D and 3D graphics. Some of our devices have video codecs for compression and decompression, H.264, 265. We have a lot of these high-speed serial transceivers, very valuable for things like PCI Express, as well as other industry standards for high-speed communication, especially in backplanes of servers. Some of our devices have this PCI Express Gen 4. Within the actual processing system, we do have all these peripherals. You'll also see PCI Express Gen 1, Gen 2 there. And then finally, our magic sauce is the programmable logic. That's what differentiates Xilinx from any other processor vendor. Programmable logic is where you can go and put these accelerators, or as I mentioned in the previous presentation, hey, if you run shorter peripherals, and let's say I'm doing an automotive application, you may only have 2 CAN interfaces up here. You may need 4 in your system. Well, guess what? You can just go and create soft peripherals in the programmable logic. So the topic of this session was for automotive application, and I'm just going to kind of give you a couple quick examples of how it can be used. So generally what happens is you'll have a bunch of information coming in. You'll have some sensors. They could be cameras, both vision-based or infrared-based. You might have radar, LiDAR, and you have all this data coming in, a massive amount of data. And generally, when you're looking at large amounts of data, general purpose processor just can't handle all that data coming in. General purpose processor can't handle video streaming all going through its compute pipeline. And so this is where programmable logic comes in. You can create this dedicated pipeline of data flowing into the system, pushing out to DDR where it can then be post-processed. On the other side, you have a general purpose types of functions. You may have a user interface, console information that needs to be displayed. You may need to be making some high-level decision making based on some of the inputs. This is where the ARM processors come in. And then you get the stuff in the middle. As I mentioned, you have this massive amount of information that's coming in, and you need to process it. Maybe you need to run through multiple neural networks, each one taking particular information from a particular sensor to make a particular inference or decision. And so that's really well done in the programmable logic. Once you've boiled all this information down, though, You may want to go through a complex decision-making process. You may have information coming in from your vision sensor that's saying, I don't see much out there. You may have something coming in from your infrared sensor that says, yeah, I see something out there, but I'm not sure what it is. You may have something coming in from the radar or LiDAR that says, yes, there's something out there. Okay, what's your decision going to be? You had your vision sensor that said, I don't see anything. Okay, what I just described, maybe it's a scenario where you've got a lot of rain, fog, camera's not doing its job, can't do its job. But things like radar and LiDAR can do a little bit better job of penetrating. So now you've got this complex set of information coming in. You've got to make a complex decision with limited information, and that's probably a place where a good general application processor could be used. So something like the R5s can be making the final decision on the information that's coming in. Send that final decision information maybe to platform management unit. Platform management unit goes and does a quick system-wide check, makes sure everything is healthy. Okay, there's been no single event upsets, nothing else that's strange going on, and then finally make that braking decision. It says go ahead and brake the car. This is an architecture, a hypothetical architecture, or a theoretical architecture for a ADAS system, for autonomous driving. And you can see what's involved in these types of systems. You'll have multiple cameras bringing information in, upwards to 6 cameras. Some of them are used in different modes. So for example, you may have forward-looking cameras that are used when you're driving forward. You may have rear-view cameras that are used when you're backing up. You may have additional side-mounted cameras that go and are used simultaneously with all the other cameras when you are doing parking. And you might want to have a 360 surround view. You may have forward-looking cameras that are both short range and long range. You may have the LiDAR and radar coming in. And as you can see, a typical type of thing, all this data comes in, it's captured, it's pushed out to DDR memory. Then you have a whole bunch of functions that may be going on that you have to do. So you may have to do things like analytics for pedestrian detection, different type of analytics for lane departure, analytics for vehicle detection in front of you, okay? Traffic sign recognition. Gee, I'm driving fast up to a stop sign and the driver hasn't noticed there's a stop sign there. So maybe I need to let him know to brake the car, or maybe I'm fully autonomous and I know I need to brake the car. Blindside spot detection. Headlamp control. Okay, all of this comes in, has to be processed and done in a very efficient manner. This is where programmable logic comes in, and then your high-level functions are typically handled by your processing system. I'm going to skip over a couple of these just because of time. All right. Most neural networks, they start out floating point. Then everybody rapidly concluded floating point's not very cost effective, extremely computative, demanding, requires a lot of logic, power hungry, so they rapidly went to 32-bit. Then they went to 16-bit, down to 8-bit. Most of the neural networks are in the 8 to 32-bit range. Our research labs went in and took a look at it and said, you know what? What happens if we go down to 4 bits, 2 bits, 1 bit? What happens? Within our devices, we always talk about LUTs. A LUT is a multi-input block that can make a decision, typically 6 inputs, single output. And they said, okay, if we're doing 32-bit operations, it might take 178 LUTs. If we're doing 1-bit operation for a neuron, it only takes 1 LUT. What's our performance? So here you can see, this is what's called a Vertex 9, ultra-scaled 9 device. We can do 100 teraops if we're doing 1-bit functions versus a single teraop if we're doing 32-bit functions. So you see there's a dramatic performance improvement, 100-fold by going down in the number of bits. And you can also see over here the relative energy cost in one of our devices for these types of functions. And then, as I mentioned earlier, one of the challenges is the weight functions and the thresholds. And your memory cost is dramatically reduced. So you can start keeping all of these weight values and functions locally. Bottom line, you save power, you save logic, you be more efficient. And again, I'm going to skip over this slide, but basically what we're saying is that we can go and automatically generate these types of functions, whether it's 8-bit, 4-bit, 2-bit. And then the obvious question comes in, gee, if I'm going down in the number of bits, doesn't my accuracy go down? The answer is absolutely, your accuracy goes down. But the good news is that by increasing your network size, you can obtain the same level of accuracy. And so, here's an example of an int2. You get a particular performance with the same amount of logic. You're going to get lower performance with a binary network, but by increasing the network size, you will be able to increase the accuracy to obtain the level you want to achieve. And the obvious question is, okay, if I were to go, let's say, from 8-bit to 1-bit, does this mean my network size increases by 8-fold, which means I really don't come ahead? And the answer is no. So you end up, as a net, having increased performance, lower power, with less logic. The design example, again, I do invite you to come by and see our demo tomorrow, was a German roadside database. You can see we did training with 50,000 images, standard database. People ask, how much does it cost? Amazon Web Server, P2X large instance, 8 hours cost about $8. And our network composed of 6 convolutional layers, 2 max pool layers, 3 fully connected layers. Performance-wise, we ran the application in software. We were able to do 2.2 images per second. Programmable logic, 19,000, 8,600 times acceleration. And then our last slide, I'll just play the video in case you didn't have a chance to see it earlier. This is what the demonstration looks like. We'll bring in an image from a scene. We will identify the sign. We will then tell you what it is and our accuracy. And sometimes we do really well, 97%, 93%. Sometimes we don't do quite as well. But the interesting one here was there were multiple signs in the scene. If you look at the number 2 choice, pedestrians in the road, it's over there. That's what happened with this particular recognition algorithm. All right, time for 1 or 2 questions. Yes?
Okay. So I think it is good presentation. So because I'm a software guy, so I'm also doing some investigation of AI software, deep learning software on ARM space, and about how to use FPGA part on such kind of platforms. So I'm not sure because you mentioned that there are a lot of cores on this board. The Cortex A53, Cortex R5, Mali GPU. So I'm trying to understand what operating systems are supported on this platform, what frameworks are supported, how to how to develop software on this board. I'm really interested in this. Yeah.
Okay, I'll give you a real abbreviated answer, and then I'd like to invite conversation in the hallway. Because I actually did cover this yesterday, but that's okay. So again, first, all this is on one chip. A53s run Linux or a collection of other major operating systems. There are 5 tends to run RTOSes. Architecturally, we're still delivering different types of design examples. Probably the most interesting aspect was we also have C to HDL tools. In other words, we have tools that allow you to take C code, find the critical code segment, and say, I want to take that, push it out into hardware, and do that in an automated manner. Okay, hit my time limit. I want to thank everyone for attending. We do have another presentation from Xilinx. I'd like to introduce Wendy, and she is going to be talking about OpenAmp.